Welcome back, everyone. In this video, we're going to talk about the capacity of steel bolted connections in shear. Throughout this video, we're going to focus on this particular example connection. This assembly is put into tension with 200 kips of factored load. There's obviously going to be a reaction back on this side, and that tension in the assembly is putting all these bolts into shear. So we want to calculate the shear capacity of this bolted connection. The cross-section is shown over on the right. We have a double angle section right here, and that's bolted or sandwiching this gusset plate in between. So there are going to be two shear interfaces where our bolts are passing through right there. Now, before we talk about numbers and capacity, we need to understand the difference between different categories of bolted connections because they will have different limit states that we need to check. The first two I'm going to group together, so snug-tightened and fully pre-tensioned. They do have different applications. You're going to use them in different situations, but capacity-wise, they're identical because they're both known as bearing connections. So bearing just means that the bolt bears on the side of the hole, and that's how we transfer load from one piece to another. The slip critical case is going to be a little bit unique because load is transferred through friction on the faying surface. So therefore, our limit states are not the same as the bearing connections. So we're going to do the bearing first, and then we're going to look at the slip critical after that. So for bearing type connections, we have three limit states that we need to look at. And the first one is really the only one that applies to the bolt itself, and that's bolt shear. So effectively, we're slicing the bolt in half along the shear plane, and that is going to be governed by the strength of our bolt. The other two limit states here are actually not bolt states specifically. They're related to the steel that's being connected together. So if we go back to our double angle connected to this gusset plate, this top one is showing the gusset plate and the double angle is below here. We're pulling on this to the left. Therefore, all of my bolts are going to have reactions going here to the right. And therefore, it's bearing on this side of the hole. So there's going to be a concentration of stresses on that side of the hole. To check those stresses at that bearing location, we are going to do a bearing check. And if it fails, you're going to have elongation of the holes in the direction of that reaction. Now, obviously, that's going to be in the opposite direction for the double angle, and that's the important thing about these checks is that we are going to have to look at it from both pieces or all pieces that are being connected together. So you're going to do a bearing check both in this case for the gusset plate and for the double angle because you could have a bearing failure in one and not the other. Tearout's going to be a little bit different because we're literally tearing the bolt out of the steel plate. So for example, this bolt could get torn out the end in that direction, or one of the interior bolts could get torn into the next adjacent hole. And this could go all the way down through all 5 bolts, or in the opposite direction in this double angle here. So that's going to be known as the tear-out failure. The two key numbers that we're going to need going forward that govern the bearing versus tear-out failures, the first one is going to be D. That's going to be this width here, D, and that governs bearing. So D is going to be the bolt diameter, and that tells you the area effectively that your stress is being concentrated over as that bolt bears on the side of the hole. Tear out is going to be governed by what's known as the clear distance LC. So that clear distance is measured from the edge of the hole to the edge of the plate if you're on the edge of your plate, or it's going to be measured from the edge of one hole to the edge of the next hole if you're in the middle of the plate. So again, that's from the edge of this hole to the edge of that hole. And effectively what we're doing is we're trying to categorize how much material it takes to break through until we get to air. Now, regardless of which limit state you're looking at, your phi factor for all of these is going to be 0.75 as long as we're in this bearing type connection. That phi factor is going to be different for slip critical connections. And likewise, if you're in ASD, then your factor of safety is just going to be a straight 2 for all cases that we're looking at here. So let's get into some details. Let's look at some bolt shear strength. This is specified in the AISC spec J3.7, but honestly, I usually just go to table 7-1 because it has all the information that we need. The first thing that you're going to need to know is your bolt designation. So it's listed here group 120, group 140, or group 150. If you're looking at past versions of the code, that's group A, B, or C. But it means the same thing. This is essentially the strength of your bolt. So group 120 is typical structural grade. 150 is a high strength bolt. The next thing that we know is this thing called thread condition. Then there's an N or an X. And what that's telling us is whether or not the threads are what is being sheared. So in this first case right here, we have the threads are N included in the shear plane. So we'll give that an N designation because in our shear plane right here, the threads are what's being sheared off. That has a reduced cross-sectional area because of the threading, so therefore you get less capacity. On the flip side, threads excluded is going to be the X case, and that's if you're shearing it through the shank of the bolt. So ideally, this is what we try to design our bolt length to accomplish, but it's not always possible. Next, you need to know your loading condition, and it's either going to be an S or a D. S stands for single shear. Both of these top two are single shear scenarios because you have one shear plane. So the shear is just right here, and that's your only shear plane. If you have two shear planes like this, that effectively divides your stress in half. So instead of dividing stress in half, we effectively just double our capacity. So this is known as the D double shear case. Last thing you need is just a bolt diameter. So you can look that up here. And then you're ready to go. Then you can look up your ASD or LRFD capacity and move on your way. So very straightforward, very easy, works pretty good. The other two are a little bit more complicated. So if we look at bearing or tear out, these used to be combined into just one single equation, but it's been more deliberately separated in more recent versions of the code. This is going to be in Spec J 3.11 or Table 7-4, 7-5. Personally, I don't love the tables for this case, so I just use the equations because, as you can see, the equations are pretty straightforward. All the bearing conditions are going to depend on this D times T area, where D was the bolt diameter, and I'll note that's the bolt diameter, not the hole diameter, but the bolt diameter, and T is the thickness of the material it's bearing upon. So that's effectively the area over which we're concentrating our stress as that's transferred into the plate. And then FU is the ultimate stress of the steel that it's bearing upon. And the difference between these three equations is just a factor. So 2.4, 3.0, or 2.0. The first one is by far the most common. So is hole deformation a concern at surface? Almost always this is going to be a yes answer. And so if that's the case, you're going to be using this first equation right here. If we really don't care about deformation of this joint at surface level loads, then we can get a little bit higher capacity, but most of the time we can just do a conservative design with the first case. The last case is special. If you have this, you have to do it. So that's long slotted holes perpendicular to the direction of force. We don't really care if deformation is a concern. If you're doing something like that, you get a reduced capacity. So it's just 2.0 times your area times the ultimate stress. Tearout's going to be very similar. We have the same three cases that we're investigating, and they just differ by a factor. Except now the area kind of looks different. So LC, that was our clear distance, and then T is still the thickness of our plate, and then it's the same FU as before. So that sums up bearing and tearout. Now, the key thing to remember with each of these three limit states is that we're actually checking them for each individual bolt. It's very likely that bolt shear is going to be the same for all our bolts. It's very likely that bearing is going to be the same for all of our bolts because we're probably using the same bolt diameter for all the bolts in a single connection. However, tearout can be different for each of your individual bolts. So all three of these limit states are calculated for each bolt individually, and then we'll check and calculate our total capacity using the minimum strength per bolt. You can mix and match different failures. So one bolt might have a shear failure, one bolt might have a bearing failure, and one bolt might have a tearout failure within the same connection. Moving on to slip critical failure modes, there's actually one limit state and one limit state only. We don't have to do bearing tearout. We no longer worry specifically about shearing the bolt. You have slip resistance, and that's it. So this is going to be in the AISC Spec J 3.9 or in Table 7-3, and personally I like using the table for this because it really streamlines our process. The equation is not that complicated, but most of these coefficients we'll have to look up in the spec. For example, this is our friction coefficient for the surface, and it depends on how you prepare it. So there's a class A, which is going to be a typical preparation, or a class B, which is going to be a more rigorous preparation, so you get a higher friction coefficient on that fang surface. Du is sort of an overstrength factor that depends on the bolt pre-tensioning, TB. HF is a factor if you have a bunch of filler plates. That basically is introducing more slip planes within your interface, which reduces your capacity. And then NS is the number of shear planes that you have, and that's the same idea as what we had before. You can either have double or single shear, and so NS is either going to be 1 or 2, depending on whether you have double or single shear. If we go to 7.3, what do we need to know? Well, obviously, first we need to know our bolt strength. You'll notice that there's different tables for each of these. So I have just shown here the group 120 bolt table. Then you'll need to know the hole type. So the changing hole type, whether you're using standard holes or long slots or short slots, will change your phi factor for these cases. So there's a variable phi factor for a slip critical joint, which is a little bit weird, but that's already all accounted for in this table. So you don't specifically need to worry about it. So if you're using a standard hole, that would just use these top numbers. You can have single or double loading. That's exactly the same as before. And once again, we have a bolt diameter. It tells us our pre-tension for the bolt if we need that value, but you can actually just go straight down here and get your capacity. And once again, this is going to be a capacity per bolt. So each bolt is applying a clamping force. So if I have 5 bolts, I'm going to multiply my capacity that I get from this table by 5. And there's no other limit states. That's actually it. Now let's go ahead and apply this knowledge to our example connection right here, where we have 5 bolts bolting this double angle to a gusset plate. We're going to start with the bearing type connection, and first we're going to look at our bolt length, because we need to be able to tell whether or not we are going to be in a included or excluded thread situation. So our bolt's going to go here. It's going to go through this section right here, and I don't know exactly where my threading is going to be. But in this case, I'm going to include a washer. That's probably just good practice anyway. It's not strictly required for a snug-tightened condition. And we're going to have a nut at the end of that. So here's our nut. And I don't know exactly where my threading is going to be, but that's what we're going to figure out. To do that, we can go to the bolt spec. If you check out the previous video on just bolting basics, I go over this in a lot more detail. So we'll go through this relatively quickly. But the bolt spec is in the back of the steel manual, and it will give you typical lengths for bolts. And it's very, very useful, actually. So in this case, we have 3/4 inch diameter bolts, and therefore the thread length is just a set 1 3/8 inches, and we're going to have a transition thread length of 1/4 inch. And you can see what those dimensions are on our little diagram of the bolt down here. So first, what we need to do is we need to decide the length of our bolt. So L is going to be the length of the bolt. And the first thing that we need to know is what's known as our grip. The grip is this distance right here. And for our grip, we're bolting together 2 1/2-inch angles and then a 3/4 inch gusset plate. So this is going to be 1.75 or 1 3/4 inches for our grip. So our bolt's got to be that long. I'm going to add a washer onto it, and a washer is typically 5/32 of an inch. And then we'll add on the necessary distance for threading. So that's given in this spec table C2-2 right here. And it says we need to add on at least 1 inch to get a nut on the end. So we're going to add 1 inch to that. And therefore our length is 2.91. Now you're not going to get any bolt in a 2.91 inches. So we're going to round that up to a 3-inch long bolt. Now what we need is the distance of our shank, and that's called LB or L body right here. So if we want to find out LB, that is going to be L, which is in this case 3 inches, minus our thread length, which is 1 3/8, and then our transition length, which is another 1/4 inch. So minus 1 3/8, and then minus another 1/4. And again, note that this L was 3 inches as we determined from before. And this is 1.375 inches. So if we measure that on here, 1.375 is going to take us all the way to this point right here. So that is going to be our LB on this bolt. And therefore we can see that is past all of our shear interfaces. So our first shear interface happens right here. That's a 1/2 inch from the head. And then our second shear interface happens right here. That's 1.25 inches past the head. So because this is greater than 1.25, all of my interfaces are excluded from the shear plane. So therefore we are in the X case for our threads. So knowing that, now we can continue on and get a capacity. And we're going to start obviously with just the bolt shear. And we'll look this up straight in the table. So our bolt shear in this table, let's say we have group 120, that's typical structural grade bolts. We know that our threads are excluded now. And we are in double shear because there are 2 interfaces, one here and one here. We also have a 3/4 inch bolt, and therefore our capacity is going to be 45.1 kips right there. So that's it. We got our bolt shear. That already has the fee factor included, so we're ready to move on to bearing and tear out. So we'll start with bearing. We have to check bearing for each piece because each piece has a different thickness. And in theory, you could also use different grades of steel for each one. Now, D is the diameter of our bolt. That's going to be 3/4 inch. So we already know that. And then T is going to be determined by which piece we're looking at. We're going to assume A36 steel, which has an ultimate stress of 58 KSI. So we're ready to go. Our double angle is going to have a thickness T of 1 inch. That's because each angle has a 1/2 inch, but both of them are going to be working together to resist this bearing. So we're going to get 1 inch out of that. And now we can calculate our capacity RN is 2.4. And I should mention that we're assuming that hole deformation is a concern at service because almost always you're going to assume that. So 2.4 times the bolt diameter of 3/4 inch times the thickness of 1 inch times 58 KSI is going to get us 104.4 kips. So let's go ahead and apply a fee factor to that of 0.75, and therefore we're going to get 78.3 kips for our capacity. Now that's bearing on the double angle, but obviously that bolt is going to bear on also the gusset plate on the other side. And the gusset plate has a lower thickness, so it's only 3/4 inch. So therefore our capacity RN is 2.4 times 3/4 inch, which is the bolt diameter, and another 3/4 inch, which is the plate thickness. And once again, it's A36 steel, so we'll use 58 KSI. And this is 78.3 kips. Fee factor that of 0.75, and once again, we're going to get 58.7 kips. So obviously that's going to control. And once you get experienced at this, you'll know that bearing is only ever going to control for the thinner thing that you're bolting together, unless you have different grades of steel. And if you have different grades of steel, then you just have to calculate it out. But if you're bolting 2 similar grades of steel, then obviously the thinner one is going to control your bearing check. Now we can move on to tear out. And tear out's going to be different, obviously, for the double angle or the gusset plate. And I did miss out on one dimension here, but let's just say that this is 1.5 inches so that I have a similar sort of symmetric connection on both sides here. I'm going to focus first on the double angle so that we can figure out what distances that we need. So for the double angle, this distance right here, let's call that LC1. And then this distance here is going to be LC2. And we can tell that that similar distance is LC2 for all these other bolt-to-bolt clear distances. Lastly, we can see that there's a distance from this bolt hole to the edge of the gusset on the other side. And because it's 1.5 here and 1.5 here, this was LC1, so this other one is also going to be LC1. First, I need my hole diameter. So if I look at a hole, that hole is going to be determined by table J3.3, which gives you the hole diameter depending on your bolt size. For a 3/4 inch bolt, we can look that up. It's going to be 13/16 of an inch. but I always add 1/16 of an inch on for a damage zone based on how they punch out this hole oftentimes. So that's going to get me a solid 7/8 of an inch. That's always conservative to assume that damage zone. We're just basically oversizing the hole slightly, even if in reality it is 13/16 of an inch big. If I want to find my distances LC1, that's just going to be 1.5 inches, and I need to subtract off the radius of the hole, so that's minus 1/2 of 7/8 inches, and therefore that is 1.0625 inches. And I'll need LC2 as well. That, as we can see here, is 2.25 inches. So 2.25 inches, and I'm going to subtract off the full radius, or excuse me, the full diameter of one hole, 7/8. And that's going to give me 1.375 inches. For convenience, I'm going to letter all of my bolts here because they will have different capacities depending on which bolt I'm looking at and depending on which direction that bolt is being pulled. So for example, in the double angle, everything is being pulled to the left. So my tear out is always going to happen this way for my double angle. So therefore, bolt A is going to get an LC1 of 1.0625. And if we're looking at bolts B through E, they're all going to have a distance of LC2. So B through E are going to be LC2 is 1.375 inches. Now we'll notice the direction of that shifts if we're looking at the gusset plate. So looking at the gusset plate, everything is going in the opposite direction here. And therefore tear out is all going to happen this way. So that means A through D are all going to use LC2. So we'll write that out. So A through D are using LC2 of 1.375 inches. And then E is going to be using our LC1 of 1.0625 inches. So we have all of our expressions. What we need to do is just plug them right in here, and I'm going to shortcut it a little bit so we don't have to write as many numbers. Our FU is still the same, 58 KSI. The double angle still has a thickness of 1 inch, and the gusset plate still has a thickness of 0.75 inches, and we're still going to be applying phi factors of 0.75 to both cases. So running through all of our numbers, we'll find that for the double angles, bolts A will have a capacity of 55.5 kips after applying the phi factor, and B through E will have a capacity of 71.8 kips. So obviously those ones are going to be higher because it has a further distance to travel to the closest edge. Now that will of course switch around when we look at the gusset plate. So A through D are going to have a capacity of 53.8 kips, and bolt E is then going to have a capacity of 41.6 kips. Now that we've checked all of our limit states, we need to combine all this information and see what are the controlling limit states for each bolt. So on a bolt by bolt basis, you can see we have our table here. Bolts A through E, as I have them labeled before, each have different capacity for each of essentially the 5 things that we've checked. We've checked bolt shear, we've checked bearing on the double angle or bearing on the gusset plate, tear out of the double angle or tear out of the gusset plate. And among these, we're going to choose the controlling one on a bolt by bolt basis. So bolt A is controlled by bolt shear, as is B, C, and D. Bolt E will tear out of the gusset plate, and that is less than our bolt shear. So that's the one that's going to happen. So therefore, our controlling case is going to be 45.1 plus 45.1 plus 45.1 plus another 45.1 plus a tear out of 41.6. And then the sum of all that is 222 kips. So that is our total BRN total right there. and that would be the governing capacity. Now, as we saw, our factored load was 200 kips, so in fact, we are good to go because that is greater than our demands. So this bolted connection works if it is a bearing type connection. The last thing that we're going to do is we're going to look at the slip critical case, because that will take us probably about 30 seconds to run. It will be actually a pretty nice little exercise to see how easy these are. So we have the same type of connection, except I'm going to classify this as slip critical with a class A fang surface. That's a typical fang surface that we're bolting together here. So we have one limit state to check. That's a slip resistance. We can just go straight to table 7-3. Of course, we're going to be looking up our group 120 bolts here. By default, this is a class A fang surface, and a footnote on the table says what to do if you have a class B fang surface. You just multiply this by a factor. We have standard holes. It's in double shear. We have 3/4 inch bolts. Therefore, it's 19 kips per bolt. And that's pretty much it. So our capacity phi Rn is 19.0 kips per bolt. And we have 5 bolts. And so therefore, this is 95 kips, which is clearly not good if we have a demand of 200 kips. So we're going to be in some trouble if we want to make this slip critical. We're going to have to slightly more than double the bolts on this connection to actually achieve that slip critical status. Now, therefore, if that's not necessary to do a slip critical connection, we're not going to do that. So that is shear strength of bolted connections in a nutshell. As always, I hope you learned something. So stay tuned. Next time, we'll be talking about bolts in tension. So I'll see you next time.